Welcome to the fourth lesson on the course Strength of Material. We are going to discuss today certain aspects of analysis of stress, which we have discussed partly in the previous lessons. In this particular lesson, it is expected that once we complete it, one should be able to evaluate stresses on any plane through stress transformation equations, evaluate principal stresses and locate principal planes for two-dimensional problems. In fact, in the previous lesson we have discussed about the evaluation of principal stresses in a three-dimensional plane. We will be discussing here evaluation of principal stresses and location of principal planes for two-dimensional problems. We will evaluate the maximum shear stresses at a point on a body for two-dimensional problems. Also, we look into the concept of Mohr circle for stress, and we will demonstrate how to construct Mohr circle for stress. Hence, the scope of this particular lesson is the derivation of the transformation equations for evaluation of stresses for two-dimensional problems, evaluation of principal stresses and maximum shear stresses, construction of Mohr circle. We will look into the aspects how we are going to draw a Mohr circle for evaluation of stress at a particular point in a stressed body. We will solve a few examples to demonstrate how the stresses can be evaluated at a particular point. Let us look into the derivations of the transformation equations. We have discussed about the plane stresses in two dimension. If we consider the stressed body at a particular point, this is our reference x axis, this is the reference y axis. The stress which is acting in the x plane is normal stress is sigma x, the normal stress in the y plane is sigma y, and the shearing stresses as tau x y. We are interested now to evaluate the stresses on a plane, the normal to which is at an angle of theta with respect to the x axis. The plane is considered in such a way that the normal direction, normal to the plane, coincides with the reference axis, which we denote as x dashed and y dashed. Since the normal to this particular plane coincides or is the parallel to the x dashed axis, we call this plane as x dashed plane. Now, let us look into the state of stress on this particular plane. If we take out this particular wedge and if we designate this as say A, B and C, the stresses which are acting on this particular part, they are sigma x, the normal stress on this surface, sigma y, the shearing stresses tau x y, this being the x dashed plane, the normal stress to this particular plane is sigma x dashed, and correspondingly the shear stress is tau x dashed y dashed. Considering the unit thickness normal to the plane of the board, and if we assume that the area on line AC, area on line AC as dA, which is length AC multiplied by the unit thickness. Considering that this particular angle is theta, this particular angle also is theta. Hence, the area on line AB can be designated in terms of the area dA, which is dA cos theta, and area on line BC can be designated as dA sin theta. Hence, the forces which are acting on these planes are the stresses multiplied by the corresponding area will give us the force. Now, if we wish to write down the equilibrium equations in the x dash direction and y dash direction, then the equation looks like this: summation of forces in the x dash direction f x dash is equals to 0. The forces which are acting in the f or the x dash directions are sigma x dash, the stress multiplied by the area dA is acting in the x dash direction, minus sigma x acting on the area dA cos theta, and the component in the x dash direction is cos theta, sigma y which is acting in the opposite direction of sigma x dash is negative sigma y dA sin theta is the force and multiplied by the component which is sin theta. The shearing stresses which we have tau minus tau x y acting on BC, which is dA sin theta, component along x direction is cos theta, minus tau x y acting on plane x, which is dA cos theta, and component along sin theta. This is equals to 0. So, this gives us the equation as sigma x dash is equals to sigma x cos square theta plus sigma y sin square theta plus twice tau x y sin theta cos theta. Writing cos square theta and sin square theta in terms of cos 2 theta, you can write this as sigma x times half of 1 minus 1 plus cos 2 theta plus sigma y times half of 1 minus cos 2 theta. Plus twice sin theta cos theta, if we write as cos 2 theta, I am sorry sin 2 theta, then tau x y sin 2 theta. So, this is equals to, we can write as sigma x plus sigma y by 2, taking this part, plus sigma x minus sigma y by 2 cos 2 theta plus tau x y sin 2 theta. So, this is the the stress in the x direction, normal stress sigma x dash, which are written in terms of the stresses sigma x, sigma y and tau x y. Similarly, if we take the equilibrium along f y dashed, if we say summation of f y dashed is equals to 0, we get tau x dashed y dashed as equals to sigma x, we can write tau x dash as equals to sigma x cos theta sin theta minus plus sigma y sin theta cos theta plus tau x y sin square theta tau x y cos square theta minus tau x y sin square theta. Hence, we can write tau x dash y dash as tau x dash y dash as equals to minus sigma x minus sigma y by 2 sin 2 theta plus tau x y cos 2 theta. So, these are the equations sigma x dashed and tau x dashed y dashed. Sigma x dashed and tau x dashed y dashed are the stresses on plane which is at an angle of theta with respect to the x axis. Similarly, if we want to evaluate the stress in the y dash direction, the normal stress sigma y dashed, the stress sigma y dashed is at an angle of theta plus 90 degree. So, if we substitute in place of theta as theta plus 90, then sine of 180 plus 2 theta is equals to minus sine 2 theta, and cos of 180 plus 2 theta is equals to minus cos 2 theta. And if we substitute these values in the expression for sigma x dashed, we get sigma y dashed as equals to sigma x plus sigma y by 2 minus sigma x minus sigma y by 2 cos 2 theta minus tau x y sin 2 theta. Thereby, if we add these two sigma x dashed plus sigma y dashed, this gives us the value as equals to sigma x plus sigma y. If you remember, in the last lesson we had discussed that the stresses sigma x plus sigma y plus sigma z is equals to sigma x dash plus sigma y dash plus sigma z dash, which indicates that irrespective of the reference axis system, the summation of these normal stresses, they are constants, which we had called as stress invariance. So, here this is proved again that the normal stresses with reference axis x dashed y dashed, sigma x dashed plus sigma y dashed is equals to sigma x plus sigma y is equals to constant, and so are the other stress invariants. Hence, we have obtained the stresses in the direction which is at an angle of theta as sigma x dash is equals to sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos 2 theta plus tau x y sin 2 theta. Also, we have seen tau x dash y dash as equals to minus sigma x minus sigma y by 2 sin 2 theta plus tau x y cos 2 theta. So, these are the transformation equations. That means, we can evaluate stresses at any plane which is oriented at an angle of theta in terms of the normal stresses sigma x, sigma y and tau x y. And please keep in mind that the rotation angle theta we have taken anticlockwise, and this is positive according to our convention. Hence, these are the stresses which we have just now derived, that sigma x dash as equals to sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos 2 theta plus tau x y sin 2 theta. Tau x dash y dash as equals to sigma x minus sigma y by 2 sin 2 theta minus plus tau x y cos 2 theta, and we have seen that sigma y dash likewise is this, and if we add sigma x dash plus sigma y dash, we get that is equals to sigma x plus sigma y. Now, let us look into that the position of the planes where the normal stresses are maximum. Now, we have obtained that the normal stress on a plane sigma x dash which is at an angle of theta is equals to sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos 2 theta plus tau x y sin 2 theta. If we take the derivative of this normal stress with respect to theta, which is del sigma x dash del theta, this is equals to minus twice sigma x minus sigma y by 2 sin 2 theta plus twice tau x y cos 2 theta. And if we set this as equals to 0, then we get tan 2 theta. If we take this on the other side, tan 2 theta is equals to tau x y by sigma x minus sigma y by 2. Now, this particular equation has two values of theta. One is, let us call that as theta p. With reference to the axis system, we have the plane which is an angle of theta p. Also, we will get another angle which is at an angle of 180 as tan of 180 plus theta is equals to tan theta. Hence, we have one as twice theta p and another angle at a distance at an angle of 180 degree plus twice theta p will give us two values. So, this is the derivative of the normal stress, and this is the values of tan theta, and we will get two values of this root, which we have said that 2 theta and 180 plus 2 theta. We have designated this as say theta p and 180 plus twice theta p. So, in effect, when we transform this into the stress part, we have angle theta p and 90 plus theta p, that indicates that we have two planes which is at an angle of theta p. Normal to this is the plane on which the normal stress is maximum, and then we have another plane which is at an angle of 90 degree with reference to this particular plane, because the other plane is at 90 plus theta p. So, these are the two normal directions where one will be the maximum and another one will be the minimum. These are the two normal stresses. Interestingly, if we look into that, the expression for tau x dashed y dashed is equals to sigma x minus sigma y by 2 sin 2 theta plus tau x y cos 2 theta. Now, if we set the tau x dashed y dashed equals to 0, then we get tan 2 theta as equals to twice tau x y by sigma x minus sigma y, which is similar to the expression which we had obtained for tan 2 theta, setting the derivative of the normal stress to 0. And since these two angles match, this shows the planes where we have obtained the maximum principal stresses, maximum and the minimum principal stresses, they coincide with the planes where the shearing stress is 0. And as we have defined before that the planes on which the shearing stress is 0, the normal stress is designated as principal stress. Hence, the maximum normal stresses which we have obtained, they are nothing but the principal stresses, where the shear stresses are 0 and their angles are defined by theta p, where we have evaluated twice theta p and 180 degree plus twice theta p. So, the maximum and minimum normal stresses, they are nothing but the principal stresses. Now, while evaluating the, let us evaluate the maximum values of these normal stresses and the principal stresses. We have seen that this angle 2 theta p, where tan of 2 theta p is equals to tau x y by sigma x minus sigma y by 2. Hence, this value of this hypotenuse r is equals to root of sigma x minus sigma y by 2 square plus tau x y square. Hence, the value of cos 2 theta p is equals to sigma x minus sigma y by 2 r, and sin 2 theta p is equals to tau x y by r. If we substitute the values of cos 2 theta p and sin 2 theta p, the expression for the normal stress which we have evaluated, which is sigma x dashed is equals to sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos 2 theta plus tau x y sin 2 theta. Now, if we substitute for cos 2 theta and sin 2 theta in terms of these 2 theta p's, this we get as the maximum stresses. So, sigma x dashed maximum or minimum which are nothing but the principal stresses sigma 1 or sigma 2 is equals to sigma x plus sigma y by 2 plus, in place of cos 2 theta p we write sigma x minus sigma y by twice r. So, this gives us sigma x minus sigma y by 2 square to 1 by r plus tau x y square by r. So, this is equals to, in fact, this particular part is sigma x minus sigma y by 2 square plus tau x y square by r, and as we have denoted r as root of this. So, r square is the top part. So, sigma 1 2 can be written as sigma x plus sigma y by 2 plus r square by r, this gets cancelled. So, this eventually gives us sigma x plus sigma y by 2 plus root of sigma x minus sigma y by 2 square plus tau x y square. So, this is the value of the maximum stress, or one of the stresses we get. Now, so we have obtained that sigma max or minimum, let us call that as sigma 1, as equals to sigma x plus sigma y by 2 plus root of sigma x minus sigma y by 2 square plus tau x y square. Now, we have seen that the normal stresses are the constant summation of sigma x plus sigma y is equals to sigma x dash plus sigma y dash should be equals to sigma 1 plus sigma 2, because these are the two normal stresses acting in two perpendicular planes. So, you can write sigma 1 plus sigma 2, the two normal stresses in two perpendicular planes, as equals to sigma x plus sigma y. Hence, sigma 2 from here is sigma x plus sigma y minus sigma 1, and sigma 1 being given by this, we can write this as equals to sigma x plus sigma y by 2 minus root of sigma x minus sigma y by 2 square plus tau x y square. Hence, the stresses sigma 1 or 2 can be given as sigma x plus sigma y by 2 plus minus sigma x minus sigma y by 2 square plus tau x y square, and these are the values of principal stresses, maximum and minimum principal stresses. So, these are the values of principal stresses sigma x plus sigma y by 2 plus minus square root of sigma x minus sigma y by 2 square plus tau x y square. Now, having looked into the maximum values of the normal stresses, which are the principal stresses, let us look into what will be the value of maximum shear stress. We have seen that the shear stress on any plane x dashed y dashed as tau x dashed y dashed as equals to minus sigma x minus sigma y by 2 sin 2 theta plus tau x y cos 2 theta. Now, if we take the derivative of this with respect to theta, then del tau x dashed y dashed by del theta gives us minus twice sigma x minus sigma y by 2 cos 2 theta minus tau x y 2 times sin 2 theta. So, tau x y sin 2 theta is equals to minus sigma x minus sigma y by 2 cos 2 theta, or tan 2 theta is equals to minus sigma x minus sigma y by 2 by tau x y. Now, here also, as we have noticed earlier, that there will be two values of theta defining the two perpendicular planes on which the shear stresses will be maximum, and those angles being twice theta s and 180 degree plus twice theta s. So, in the stressed body it will be theta s plus 90 and theta s and theta s plus 90. These are the two perpendicular planes on which the shear stress will be maximum. Now, if we look into the values of this tan 2 theta s and compare with the previously calculated value of tan 2 theta p, we find that tan 2 theta s is nothing but equals to 1 by tan 2 theta p. Tan 2 theta p we had evaluated earlier as tau x y by sigma x minus sigma y by 2. So, this is equals to minus cot twice theta p, which we can write as tan 90 plus 2 theta p. So, this indicates that 2 theta s is equals to 90 plus 2 theta p, or theta s is equals to 45 degree plus theta p. So, this indicates that the maximum shear stress occurs in the plane which is at an angle of 45 degree with respect to the maximum or minimum principal stresses. So, this is the value of tan 2 theta which we have just evaluated, and hence we find that two mutually perpendicular planes on which the maximum shear stresses exist, and maximum and minimum shear stress form an angle of 45 degree with the principal planes which we have just seen. Now, let us look into that if what is the value of the principal stress where their shear stress is maximum. Now, we have calculated that tan 2 theta as equals to minus sigma x minus sigma y by 2 by tau x y. So, if we place this in a geometrical form, this we have said 2 theta s. So, this angle 2 theta s is, this is tau x y and this is minus sigma x minus sigma y by 2. Hence, the value of r again as equals to root of sigma x minus sigma y by 2 square plus tau x y square. So, likewise then the cos theta or rather cos 2 theta s is equals to tau x y by r, and sin 2 theta s is equals to minus sigma x minus sigma y by 2 r. Now, if you substitute the values of cos and sin in the normal stress, which is sigma x dashed is equals to sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos 2 theta plus tau x y sin 2 theta. Now, in place of cos 2 theta and sin 2 theta, if we substitute the values of cos 2 theta s and sin 2 theta s, we will get the value of normal stress, and also we will get the values of shear stresses on these planes. Now, if we substitute these values, we get this as equals to sigma x plus sigma y by 2, because these two terms gets cancelled once we substitute these values. Also, we have seen the values of shear stress tau x dashed y dashed is equals to minus sigma x minus sigma y by 2 sin 2 theta plus tau x y cos 2 theta. And if we substitute the value of sin 2 theta and cos 2 theta, we get this as equals to root of sigma x minus sin 2 theta we have obtained as sigma x minus sigma y by 2. So, this is sigma x minus sigma y by 2 square of this times 1 by r plus tau x y square by r, and r being root of sigma x minus sigma y by 2 square plus tau x y square. So, this is equals to root of sigma x minus sigma y by 2 square plus tau x y square. In fact, this gives us the tau max. In fact, the minimum stress is the negative of this. So, tau max or mean, we can write this as plus minus root of sigma x minus sigma y by 2 square plus tau x y square. So, these are the value of maximum stresses, and as we have observed that the value of the principal normal stress on the plane where shear stress is maximum is equals to sigma x plus sigma y by 2. Now, if the normal stresses are the principal stresses, then we get that the maximum shear stress as equals to sigma 1 minus sigma 2 by 2 from this expression. If sigma x is sigma 1 and sigma 2, sigma y is sigma 2, and this being the principal stresses, tau x y will be 0. So, tau max gives us the value in terms of principal stresses as sigma 1 minus sigma 2 by 2. This is the maximum shear stress in terms of the normal principal stresses. And hence, we say that the planes of maximum shear stresses are not free from normal stresses. As we have seen in case of principal stresses, the principal stresses acts on the planes on which the shear stresses are 0, whereas the planes on which the shear stresses are maximum, there we do have normal stresses, and the value of the normal stress as we have seen is sigma x plus sigma y by 2. Now, let us look into another representation or evaluation of stress from a concept which was given by Otto Mohr of Germany in 1895, which we popularly designate this as Mohr circle of stress. Now, as we have seen, if we have a stressed body in which the normal stresses are sigma x and sigma y, and we have the corresponding shear stresses. Now, we can represent this stress system in terms of the circle. Now, let us look into the expression for the normal stress and the shearing stress. Sigma x dashed as equals to sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos 2 theta plus tau x y sin 2 theta, and tau x dashed y dashed is equals to minus sigma x minus sigma y by 2 sin 2 theta plus tau x y cos 2 theta. And from the first of this equation, we can write this as sigma x dashed minus sigma x plus sigma y by 2. This is equals to sigma x minus sigma y by 2 cos 2 theta plus tau x y sin 2 theta. Now, if we square this equation and the second of this equation and add them up, we get sigma x dashed minus sigma x plus sigma y by 2 square of this plus tau x dashed y dashed square of it. This is equals to, if we square this term, we get sigma x minus sigma y by 2 square and sin square 2 theta cos square 2 theta becomes 1 plus tau x y square, and the other term gets cancelled. This particular equation can be represented as x minus a square plus y square is equals to b square, and this particular equation is well known equation, which is that of a circle, where the center of the circle lies at plus a 0 at the coordinate plus a 0, and the radius of which is equals to b, and x represents sigma x dashed and y represents tau x dashed y dashed. So, in the circle, if we draw a circle whose center is at a 0, where a is sigma x plus sigma y by 2 on the sigma x dashed axis, which is representing x, with the radius of b, which is root of sigma x minus sigma y by 2 square plus tau x y square, then we get the circle, and that is what is represented here in terms of the Mohr circle. So, as we have seen that the center of this particular circle is at a distance of from the origin. If we consider this as sigma x dash sigma x axis or sigma axis and tau axis, then this is at a distance of sigma x plus sigma y by 2, the average stress. This particular point represent the stress which we have at this particular body sigma x sigma y, and the tau x y. This particular point on this particular circle represents the values of x y, which is nothing but sigma and tau at a particular orientation, which is representing a plane. Here this particular point, we are representing this as sigma x and tau x y, the sigma x and tau x y on this circle, which is representing this particular plane. Hence, since this being sigma x and this being sigma x plus sigma y by 2, the distance here, this particular distance is sigma x minus sigma x plus sigma y by 2, which is sigma x minus sigma y by 2, and this is tau x y, this particular distance is tau x y. So, eventually this particular distance is root of sigma x minus sigma y by 2 square plus tau x y square, which is that of our radius, which is b. This particular point represent the maximum normal stress on this normal stress axis. This is the maximum normal stress, this is the minimum normal stress, and from this plane if we rotate 2 theta p angle, we get one of the maximum normal stress plane, and then if we rotate by another 180 degree, we get another plane representing the maximum normal stress, and this maximum normal stress we call as maximum principal stress, which we have represented as sigma 1, and this we represent as the minimum principal stress, which is sigma 2. This particular point and this point in the circle represents the maximum value of the shearing stress tau x y, which is equal to the radius which we have just evaluated, which is sigma x minus sigma y by 2 square plus tau x y square. So, plus tau and the minus tau is the maximum and the minimum shear stresses. And if we look into the planes, this particular plane is representing principal stress, this particular plane is representing maximum shear stress, and the angle between these two is 90 degree, which is twice of that in the body. And as we have seen that the angle between the maximum principal plane and the plane on which maximum shear stress acts, they are at an angle of 45 degree, which is being represented from here. 2 theta p is equals to 90. So, theta is equals to 45 degree. Hence, from the Mohr circle we can observe that maximum normal stress is sigma 1, which we have designated as maximum principal stress, and the minimum stress is sigma 2, is the minimum principal stress, and at those two planes we have seen that no shear stresses exist, because that being on the sigma axis, the values of shear stresses are 0, and hence they are the principal stresses. Also, we have seen that the maximum shear stress is equals to the radius of the circle, which is sigma x minus sigma y by 2 square plus tau x y square, and the radius is nothing but equals to, in terms of sigma 1 and sigma 2, as sigma 1 minus sigma 2 by 2, which we have seen earlier through our transformation equation as well. Also, if sigma 1 and sigma 2 are equal, then the Mohr circle reduces to a point and there are no shear stresses developed in that xy plane. And if sigma x plus sigma y equals to 0, as we have seen that the center of the circle is located at a distance of plus a 0, which is on the sigma axis, and plus a is nothing but equals to sigma x plus sigma y by 2, the average stress. Now, if sigma x plus sigma y is 0, that means the center coincides with the origin at 0 0 point of the sigma tau reference axis, and hence at any point which is at any plane on the circumference of the circle, which is representing any plane at particular orientation, the values which we will get at the maximum principal stress as tau and also the maximum stresses as tau, and this we call as a state of pure shear, that the maximum and the minimum principal stresses are also equivalent to the maximum shear stress. So, these are important observations from the Mohr circle. Now, let us look into that how do we construct a Mohr circle. Basically, what we need to do is that if we know the stresses sigma x, sigma y and tau x y at a particular point, then we should be able to evaluate the stresses at any plane which are sigma x dash, tau x dash, tau y dash from the orientation of the plane with reference to the x plane. Now, those stresses can be evaluated either from the transformation equations as we have just seen, or we can evaluate the stresses from the Mohr circle as well. Now, let us look into how do you construct the Mohr circle based on the given state of stress. Now, let us say that at a stressed body, we know the stresses sigma x, sigma y and tau x y. As we have seen that the center of the circle is located at a distance of sigma x plus sigma y by 2. So, the center of the circle is located. Now, in this there are two ways of constructing the circle. One is either we can represent sigma in this direction and tau in the positive direction, as we have noted earlier. In that case, the angle will be in a clockwise direction. The theta angle in this Mohr plane will be in the clockwise direction, which is opposite to the convention which we have assumed while deriving this transformation equation, where we have taken theta as anticlockwise. Another way to construct the Mohr circle is that we take sigma in the positive x direction and tau in the opposite direction. In that case, the representation of the angle in Mohr plane will be in the anticlockwise direction, which matches with our convention of the transformation equation. So, let us represent the sigma in the positive x direction and tau in the lower direction as a positive. Thereby, the angle will be represented in an anticlockwise form, which we consider as a positive and which matches with our physical stress system. Now, if we represent these stress sigma and tau on this particular plane, we represent sigma and tau, thereby this particular point on the circle represents this plane, plane A, where the normal stress is sigma and shearing stress is tau. Likewise, in the perpendicular plane we have stress as sigma y and the tau shearing stress as tau, which is at an angle of 90 degree with respect to this A plane. So, in the Mohr circle, if we go 180 degree with respect to this, we get another point which is plane B, where we have sigma y and tau x y. Now, this, if we take the center as this O and radius as OA and OB and plot a circle, this gives us the Mohr circle, wherein this point represents the maximum normal stress sigma 1 and this represents the minimum principal stress, which is sigma 2. Now, if we are interested to find out the stress on any plane whose normal to this particular plane is oriented at an angle of theta. Now, this particular plane is represented by this point A. So, from here if we move at an angle of 2 theta and if we join from the center to this, the point which we get on the circle represents the plane normal to which is at an angle theta with x plane, and thereby the stresses which it acts over here, this is the normal stress and this is the shearing stress on this particular inclined plane, and that is how we compute stresses from the Mohr circle. Well, having known about the principal stresses from transformation equation and through the Mohr circle, let us look into some of the problems. Now, before we go for the problems on the normal stresses using Mohr circle, let us look into the problem which I had discussed last time and I had asked you to compute. I hope you have already obtained the values for this. Now, let me explain how to evaluate the mass which can be safely supported by the wears. Now, if we take the free body diagram of this particular part, then here there will be a force F1 to balance it, reactive forces, here there will be a force F2 to balance it. Now, if we draw the free body diagram of this whole part, then we have F1 in this particular direction and F2 in this particular direction and the mass which is hanging from this particular point. Let us call that force as mg. Now, this angle, let us call that as theta 1 and this is theta 2. From the data given, you can compute cos theta 1, which will be equals to 0.6 and sin theta 1 as equals to 0.8, cos theta 2 as equals to 0.923 and sin theta 2 as equals to 0.385. Now, if we take the summation of horizontal forces as 0, that gives us F1 cos theta 1 as equals to F2 cos theta 2. Now, it has been indicated that the maximum stress, tensile stress that the wires can withstand is 100 MPa and the cross sectional area of these two wires are given. Thereby, if we compute, F1 will give us the area times stress, which is equals to 40 kilonewton and F2 thereby is equals to 20 kilonewton. Now, from this expression 1, if we substitute for the values of cos theta 1 and cos theta 2, we find that if we substitute for F2, which is, or for F1, which is equals to 40 kilonewton. So, F2 thereby will be equals to 40 times 0.6 divided by 0.923, which is approximately equals to 26 kilonewton, which is greater than 20 kilonewton. So, instead of using F2, let us use F1. So, F1 if we represent in terms of F2, this is 20 times 0.923 divided by 0.6, which is less than 40. Hence, if we compute the values, if we take the summation in the vertical direction, summation of forces, we get that mg is equals to F1 sin theta 1 plus F2 sin theta 2, and thereby the value of m from this you get as 3293.4 kg. Well, you can look into this particular problem. You can compute the state of stress using transformation equation. Also, you can use the same problem to solve through Mohr circle of stress. These questions which we had posed last time, they are quite straightforward. The first one is maximum normal stress and shear stress in an axially loaded bar, which we know as P by A is the normal stress and P by 2A is the shear stress, and thereby tau the shear stress is equals to sigma by 2, half the normal stress. Stress invariance we have discussed today, and the value of shear stress on principal plane is 0. Well, to summarize, what we have done in this particular lesson is we have developed the transformation equations for evaluation of stresses for 2-dimensional problems, evaluation of principal stresses and maximum shear stresses. We have shown how to construct a Mohr circle for evaluation of the stress and some example to demonstrate the evaluation of stress at a point, and some examples I have set in for you to solve it. And these are the questions: that what is meant by the state of pure shear, what is the coordinate of the center of Mohr circle and what is its radius, and what happens if sigma x plus sigma y equals to 0 and sigma 1 is equals to sigma 2. We will discuss these questions in the next lesson. Thank you.